Every second of your life seems simple. A clock ticks, another second passes, another minute disappears into the past. It feels natural to believe that time flows the same way everywhere in the universe. Whether you are standing still, walking down a street, or flying across the ocean, time appears steady and reliable. But physics reveals something astonishing. This comforting belief is not actually true. Time is far stranger than our everyday experience suggests. Imagine two identical clocks. One remains on Earth while the other travels aboard an incredibly fast spacecraft. When the spacecraft returns, something unexpected happens. The traveling clock shows less time has passed. It has ticked more slowly. To someone living inside the spacecraft, nothing unusual seemed to happen. Their heart beat normally. Their watch moved normally. Yet compared to people on Earth, their time moved differently. At first glance, this sounds impossible. Time feels universal, almost sacred. But nature does not follow our intuition. The faster an object moves, the more dramatic this effect becomes. At ordinary speeds, the difference is tiny, almost impossible to notice. Yet as motion approaches the speed of light, the effect grows enormous. This strange behavior hints that time itself is not fixed. Speed quietly reshapes it. And once we begin exploring why this happens, we discover that our deepest assumptions about reality may be wrong. For centuries, scientists believed time was absolute. A second on Earth was the same second everywhere else in the universe. Motion could change speed or position, but time itself remained untouched. This idea felt obvious because everyday experience seemed to confirm it. If two people carried clocks and one walked across the room, both clocks would still tick together. Nothing about simple motion appeared to disturb time. Classical physics, especially the work of Isaac Newton, treated time as a universal background. According to Newton, time flowed steadily everywhere, like a cosmic clock that no object could influence. Space could stretch infinitely, objects could move through it, but time always marched forward at the same pace for everyone. For a long time, this idea worked beautifully. It explained motion, gravity, and the behavior of planets with extraordinary accuracy. But toward the end of the 19th century, a strange problem began to appear. Experiments studying light revealed something deeply puzzling. No matter how fast the observer moved, the speed of light always appeared exactly the same. If you moved toward a beam of light, you might expect it to appear faster. If you moved away from it, you might expect it to appear slower. That is how ordinary speeds behave. Yet light refused to follow this rule. This result was confirmed in famous experiments, such as the one performed by Albert A. Michelson and Edward W. Morley in 1887. Their measurements showed that the speed of light remained constant regardless of Earth's motion through space. The finding was shocking. If the speed of light never changes, then something else must adjust to keep that speed. Scientists struggled to understand the implication. If motion could not change the speed of light, then perhaps our assumptions about space and time themselves were wrong. The puzzle lingered unresolved, quietly hinting that the universe was far stranger than classical physics had imagined. At the beginning of the 20th century, a young physicist named Albert Einstein approached the puzzle from a completely different angle. Instead of trying to force light to obey the old rules, he asked a more daring question. What if the rules themselves were wrong? Einstein started with a simple but powerful assumption. The speed of light is always the same for every observer, no matter how they move. This idea seems harmless at first, but it carries astonishing consequences. If the speed of light cannot change, then something else must adjust to preserve that constant value. And the only things left to change are space and time themselves. Imagine two observers watching the same event while moving at different speeds. In everyday thinking, they might disagree about position or motion, but they would always agree about time. Einstein showed that this belief cannot survive if the speed of light is constant. Instead, time becomes flexible. It stretches and compresses depending on how fast an observer is moving. This effect is known as time dilation, one of the central predictions of special relativity. According to this theory, a moving clock runs slower compared with a stationary one. To the traveler carrying the clock, everything feels normal. Their seconds pass naturally, their heartbeat remains steady, and their life unfolds without any strange sensation. Yet, from the perspective of someone watching from outside, that clock ticks more slowly. The faster the motion, the greater the effect. At speeds approaching the speed of light, time can slow dramatically. In extreme situations, a journey lasting a few years for a traveler could correspond to decades passing for people who remain behind. Time, once believed to be universal, becomes personal. Einstein's insight transformed physics. Space and time were no longer independent stages on which events occurred. They became intertwined parts of a single structure known as spacetime. Motion through this structure changes how time flows. What once seemed absolute now depends on perspective. With this realization, the mystery surrounding light suddenly made sense. The speed of light remains constant because space and time themselves adjust to protect that rule. And once this door is opened, an entirely new picture of reality begins to emerge. As speeds climb closer to the speed of light, the strange effects predicted by special relativity become impossible to ignore. Time does not merely drift slightly out of sync. It begins to separate dramatically between observers moving at different speeds. The faster something travels, the more slowly its clock runs compared with clocks that remain still. Imagine an astronaut traveling in a spacecraft that moves incredibly fast, approaching the speed of light. Inside the spacecraft, everything appears completely normal. The astronaut's heartbeat stays steady, their thoughts unfold naturally, and their watch ticks exactly as it always has. From their perspective, nothing about time feels unusual. Life continues moment by moment without any obvious distortion. But an observer watching from Earth would see something very different. To them, the astronaut's clock would appear to tick more slowly. Every second inside the spacecraft would stretch longer compared with seconds on Earth. As the spacecraft moved faster and faster, this difference would grow more dramatic. Time aboard the spacecraft would seem to crawl. This effect is not a theoretical curiosity. Experiments have repeatedly confirmed it. Extremely precise atomic clocks flown aboard fast aircraft have returned showing tiny but measurable differences compared with identical clocks left on the ground. Even particles created in high-energy accelerators live longer when they move near light speed, exactly as relativity predicts. If a spacecraft could travel close enough to the speed of light, the difference could become enormous. An astronaut might experience only a few years during a long journey, while decades or even centuries pass on Earth. When they returned home, they would find a world that has aged far more than they have. This possibility is sometimes illustrated by the famous twin paradox. One twin remains on Earth while the other travels on a near light speed journey. When they reunite, the traveling twin is younger. The effect sounds like science fiction, yet it follows directly from the mathematics of relativity. At these extreme speeds, time itself behaves almost like a flexible dimension rather than a rigid ticking clock. Motion reshapes the flow of time, stretching it for some observers and compressing it for others. The closer we move toward light speed, the more dramatically reality diverges from everyday intuition. And this strange behavior hints that time may not be the universal river we once imagined, but part of something deeper and more mysterious. When we first hear that time slows down near light speed, it sounds like a strange trick of mathematics, but the deeper message is far more profound. The discovery reveals that time is not a universal rhythm shared by the entire cosmos. Instead, time is woven together with space into a single structure scientists call spacetime. In this picture, every object traces a path through space-time as it moves. Motion does not simply change position in space, it also changes how quickly time passes for that object. What we experience as the steady ticking of seconds is really just one particular path through this larger structure. This idea was one of the most powerful insights of Albert Einstein. His work showed that time behaves more like a dimension of reality rather than an invisible clock. When motion becomes extreme, especially near the speed of light, the geometry of space-time reshapes how events unfold. Because of this, two observers moving differently through space-time may disagree about the timing of events. One person's present might be another person's past or future. The universe does not provide a single master clock keeping everyone synchronized. Instead, each observer carries their own timeline shaped by motion. This realization changes how we think about the cosmos. The slowing of time is not just an odd prediction of physics. It is evidence that reality is far more flexible than our everyday senses suggest. Space and time are not rigid backgrounds, but dynamic parts of the universe itself. And once we accept that time can stretch and bend, a remarkable picture emerges. The universe becomes a vast fabric where motion shapes experience, where clocks do not always agree, and where even the passage of time depends on the journey you take through space-time.